The world we live in, a world of instant communication, intelligent devices, previously unimaginable convenience, runs on something almost invisibly small. Microchips, those tiny slivers of silicon etched with billions of microscopic transistors, are the true engines of the 21st century. They are the silent brains inside our smartphones, the command centers in our cars, and the workhorses powering the vast data centers that form the backbone of the internet. Without them, the complex digital tapestry of modern life would simply unravel. It is this fundamental importance that has transformed these minute components from mere technological marvels into objects of immense geopolitical significance, akin to oil in the 20th century. For any nation with aspirations of global leadership, mastering the art of the chip is no longer an option. It has become an absolute necessity. This is the very heart of the challenge that China has embraced with ferocious determination. The nation's leadership has publicly declared that technological self-reliance is a cornerstone of its national security and economic future. And at the very peak of this technological mountain sits the semiconductor industry. To this end, China has embarked on one of the most ambitious and expensive industrial campaigns in human history, pouring hundreds of billions of dollars into a national effort to build a world-class end-to-end chip industry from the ground up. China's national strategy for semiconductors is born from a clear and powerful vision to achieve technological sovereignty. The country's leaders view their dependence on foreign-made chips not just as an economic vulnerability, but as a critical national security risk. That view was reinforced by trade disputes when giants like Huawei were cut off from American components. The message landed in Beijing. To control its destiny, China must control chip production. Self-sufficiency means reducing imports for consumer electronics, reducing imports for advanced military hardware, and protecting technological progress from geopolitical throttling. To make it real, Beijing has a multi-pronged plan. A primary goal: increase domestic chip production across all tiers. Fabricate a large percentage of the chips it consumes, especially for telecommunications, automotive, data infrastructure. That means building more factories and upgrading the technology inside them. The plan pushes homegrown chip designs for many applications, starting with processors for supercomputers. One of the most formidable obstacles in China's path is not technological but political. United States, Japan, the Netherlands, has grown increasingly concerned about China's technological rise and its potential military applications. In response, they have constructed a complex web of trade restrictions and export controls designed specifically to slow down China's progress in advanced semiconductors. These rules are not a blanket ban, but are surgically targeted at the most critical choke points in the chip-making process. The primary focus has been on restricting China's access to the cutting-edge tools needed to manufacture chips at the most advanced nodes, features smaller than 14 nanometers, essential for high-performance computing and artificial intelligence. These restrictions place Chinese companies in an incredibly difficult position. The global semiconductor supply chain is a marvel of specialization, with a handful of companies holding near monopolies on essential technologies. ASML is the world's only producer of extreme ultraviolet (EUV) lithography machines, the indispensable tool for making the most advanced chips. Without access to these machines, it is practically impossible to compete at the leading edge. American firms dominate other critical tools. Lam Research Applied Materials. No company better illustrates China's chip predicament than its national champion, Semiconductor Manufacturing International Corporation, SMIC. As China's largest and most advanced contract chip manufacturer, SMIC was positioned as the country's best hope for catching up to global leaders. Taiwan's TSMC, South Korea's Samsung. For years, SMIC made steady progress, moving down process nodes and demonstrating growing capabilities. Then everything changed when it was placed on the US Entity List. The designation severely restricted access to advanced American tech and equipment. That effectively built a wall around its most ambitious R&D programs. The impact was immediate and profound. Without access to the latest lithography machines and essential tools, SMIC's roadmap to 7 nanometers and beyond was thrown into disarray. SMIC pivoted, focusing resources on mature, less advanced nodes, like 28 nanometers and older. While these technologies are far from obsolete, microcontrollers, power management chips, automotive sensors, they don't compete at the high-performance frontier. SMIC now exists in two realities: profitable legacy producer, but locked out of the cutting edge. That reflects a broader challenge for China's industry. Scaling up production. Building and running a modern fab is an immense operational challenge. They require an uninterrupted supply of hundreds of specialized chemicals and gases, a perfectly stable power grid, and an army of highly skilled technicians in ultra-clean environments. Faced with mounting external pressure and technological roadblocks, China's response has been nothing short of a full-scale national mobilization. The government has doubled down on its strategy of self-reliance, initiating a massive campaign of investment and policy support aimed at forging an independent semiconductor industry. The primary weapon in this campaign is capital. Through its big fund and various provincial-level investment vehicles, Beijing has injected hundreds of billions of dollars directly into the sector. This money flows to a wide array of companies, established players like SMIC Huahong Semiconductor, to a vibrant ecosystem of hundreds of ambitious startups, each tackling a different piece of the complex semiconductor puzzle. This flood of state-backed funding is designed to achieve three main objectives. The first is to accelerate research and development across the board. Huge grants are being awarded to universities and national laboratories to pursue fundamental breakthroughs in materials science, transistor architecture, and novel manufacturing techniques. Despite the immense challenges, China's relentless push has yielded tangible results and moments of genuine breakthrough. The country is now a formidable force in certain segments of the semiconductor value chain. For instance, Chinese companies have become world leaders in the back-end processes of assembly packaging testing. These steps may not be glamorous, but they are essential and profitable. China also dominates manufacturing in solar panels, LEDs. These sectors rely on semiconductor principles, but are less demanding than advanced logic chips, showing China's ability to scale production in targeted areas. In advanced areas, progress shows in specialized chip design. Tech giants have built competitive custom chips for AI. AI accelerators from Alibaba Baidu are optimized for machine learning and neural networks, powering cloud computing and surveillance systems. In 5G, Huawei's HiSilicon once designed world-class smartphone processors. As of today, October 31, 2025, China's Great Chip Race remains one of the most compelling and consequential stories in the global economy. The narrative is a complex duality of undeniable progress and formidable obstacles. On one hand, China has demonstrated its unwavering commitment, leveraging its vast financial resources and political will to build a more resilient domestic industry. It has nurtured real expertise in chip design for specific applications like AI, and has shown surprising ingenuity in working around sanctions. The nation's ability to scale production in mature technologies is proven, and it is steadily reducing its reliance on foreign chips for a wide range of everyday electronics. On the other hand, the highest peaks of the semiconductor world remain shrouded in mist. The path to the cutting edge, the 3-nanometer nodes and beyond, is blocked by a technological wall fortified by geopolitical alliances. The dependence on foreign-made, ultra-specialized manufacturing equipment remains the industry's Achilles heel. While domestic toolmakers are working tirelessly, they are in a race against a moving target. Leading edge versus mature nodes. On one side, 3-nanometer class today, pushing toward 2-nanometer and below. On the other, 28-nanometer, 40-nanometer, 65-nanometer and up, the workhorses that ship by the millions. Manufacturing first. China is strong at mature nodes. Capacity, yield, cost discipline. At the leading edge, access to EUV lithography is limited. Domestic attempts lean on advanced DUV multi-patterning. It works, but adds steps, lowers throughput, strains yields. Design next. China produces competitive custom chips for AI at the edge, and for specific domains. Yet the bar for top GPUs is set by Western leaders. And for data center accelerators. EDA is a pillar here. China historically relies on foreign tool chains. Domestic EDA is improving, expanding coverage, closing gaps, but not complete. Equipment and materials. EUV scanners remain the critical choke point. Deposition tools, etch tools, metrology tools still trail best in class. Coverage is expanding in areas that don't require EUV. Packaging and back-end. OSAT volume is a strength. Advanced packaging is progressing. Chiplets, 2.5D fan-out. Frontier implementations remain ahead elsewhere. Memory versus logic. NAND shows momentum. DRAM entrants are building capability. At the very top tiers, gaps remain. For logic, the leading edge is still the hardest hill. Bottom line. China leads or competes in volume and mature segments. A gap persists at the bleeding edge. Tools, IP, ecosystem depth. Progress is step by step. Timelines hinge on equipment access. Yields. The maturity of the broader stack. Scale grows. The wall of EUV stands. Both truths shape what comes next. A quiet takeover is happening, not at the bleeding edge, but in the sheer volume of chips the world actually uses. China's vast domestic demand, smartphones, EVs, a sea of connected devices feeds high-volume, cost-competitive production at legacy nodes like 28 mates, 40 and 65 metin. Foundries scale what the market needs most. Power management, ICs, microcontrollers, sensors, analog parts, display drivers, steady, repeatable, and everywhere. This is where capacity wins. Mature lines running around the clock, optimized for yield, optimized for reliability, optimized for price. Packaging and test are a force multiplier. OSAT houses lead in volume, advanced packaging inches forward. Chiplets 2.5D fan-out for domestic systems. The result? Faster turnaround from wafer to module, enabling rapid product cycles for phones, EVs, edge devices. Memory is gaining momentum. Competitive NAND ramps, new DRAM entrants not yet top of class, but closing essential gaps. On the factory floor, domestic equipment and materials fill more steps. Deposition, etch, metrology chemistries, especially where EUV isn't required. The design ecosystem accelerates. Custom AI accelerators, cloud accelerators, domain-specific silicon for surveillance, domain-specific silicon for edge, fast-growing fabless startups. Policy is the flywheel. Subsidies, tax breaks, university pipelines, local support compress timelines for new fabs and expansions. All of this compounds. Demand creates scale, lowers cost, lower cost, attracts more design wins, and the cycle repeats. China's takeover is about scale and breadth. Dominance in volume packaging, mid-tier supply chains, while the leading edge remains challenging and progress continues step by step. The road ahead is technical and tactical. Today's bottlenecks are clear. EUV scanners are blocked, pushing advanced DUV multi-patterning. Domestic deposition etch chemicals subsystems are improving fast. Metrology still trails below 14 nanometer. Photoresists, mask blanks, specialty gases are advancing, but quality is mixed at leading nodes. What in trouble means? High capex burn tool delays yield drag from extra DUV steps. Export controls expand maintenance parts at risk. Talent churn pressures roadmaps. Financing faces scrutiny after past overbuilding. Governance is improving unevenly. Timelines, indicative, 2025-2027. DUV immersion scales at 2380. Local share in deposition, etch hits 50-70%. Multi-patterned DUV touches 1410 nm in limited runs. Metrology solid at 28 meets, partial at 14 May. 2028-2032. Domestic DUV competitive at 14 to 7 nm in select fabs. Broader local resists, masks and gases. Yield gaps persist at 7 nanometer. EUV remains R&D. 2033-2038. Prototype homegrown EUV possible, throughput and uptime lag. Advanced metrology narrows but still behind. Beyond 2038, a full domestic stack is feasible in optimistic cases, parity uncertain. Scenarios: optimistic 7 nm DUV competitive GUI 2030, pilot EUV or is 2035, wider EUV post 2036-2038. Base strong 40 nm by 2028, selective 7-10 nm by 2031-2033, EUV pilots post 2036 plus, constrained mature node dominance, advanced logic tight, EUV slips beyond 2040. Bottom line, China can own much of the non-EUV toolchain this decade. Leading-edge parity hinges on EUV class tools and metrology depth, likely mid to late 2030s or later.